Good morning, good afternoon, and good evening. I am Viral Vigela, and I'm the account manager of X-ray CT technology with Rigaku. I'm here with our presenters, Angela Criswell and Aya Takase.
Hey, everyone.
Thank you all for attending Rigaku's webinar series, Ask the Expert. The best way to learn something new is talking to an expert. Our series will cover various topics and will be joined by industry experts to help us better understand CT techniques. Today, we want to welcome Dr. Arne Jacob, application engineer at Math to Market. We'll be discussing when and how to use digital rock physics and simulations in rock properties for oil and gas applications. But before we start, a few housekeeping items. For today, this is going to be an interactive session, and I'll be posting relevant links in the chat window. We'll take your questions live during the webcast and answer them during the session, so please don't wait until the end to ask. As usual, please submit your questions via the Q&A button at the bottom of your screen. We won't be monitoring the raised hand function, and we'll try to get through as many questions as we can during the webinar, and any unanswered questions will be answered after the session is completed. If for whatever reason you have difficulty viewing the webinar live, please note it is being recorded and you will be able to view the recording beginning tomorrow. With that being said, let me turn it over to Angela and I.
Thank you, Viral. And thank you, Arne, very much for joining us. It's great to have you back. Now, are you ready to share your screen?
Yes, Aya, thank you.
Okay, so let me stop on my side.
Yes. So can you see my PowerPoint presentation now?
Yes.
Yes.
Okay, so we have many questions we want to ask you, Arne, today, but let me start with this one. So why do you need a CT in the oil and the gas industry?
So thank you, Aya, for your question. So for me, as somebody who is coming from the digital rock physics side, we would use CT to obtain high quality imaging data of our samples we took from reservoirs. The ultimate goal on each digital rock physics workflow is to understand the reservoir properties better and to optimize the oil and gas extraction. At the beginning of such a workflow would be that you drill a sample from your reservoir and image it by, for example, micro-CT. That can be, of course, a Rigaku device, which you're using then. And your goal is then that you obtain a high quality image data of that sample, which can be treated as a digital twin of your original sample you've drilled from your reservoir. After you've obtained these gray value image data, you can then do some post-processing on these data to get rid of artifacts which are almost anyways or anywhere in that micro-CT scan and obtain therefore the best possible amount of information. Afterwards, you can simulate by some simulation software, for example, Geodict, you can simulate to analyze certain kind of parameters of that image stack. That may be morphological properties, but also flow properties like permeability, flow resistivity, two-phase flow, electrical conductivities, and so on. And by upscaling the data you have from that plug or core scale, you can then insert this data you have into your reservoir simulator, which gives you a very good prediction of how to treat your reservoir in the best possible way. So in a nutshell, that would be that digital core analysis improves the understanding of reservoir properties, which you would need to extract the oil in the best possible way. And second, it digitalizes special core analysis, which normally takes a huge amount of time and costs. And with the digital approach, you can save that time and costs in comparison to your experiments in the best case. Are there any questions to that slide?
Yeah, we have a question here. Hang on. My apologies. My screens are all over the place.
That's why I'm in the office, because I have multiple screens here.
I just recently changed my setup, so it's kind of, but
No.
it's what was the DRP? When was DRP invented and implemented in the practical decision-making process?
Yeah. So it's hard to tell who invented DRP originally, because many of the advances in DRP came over time or were invented even now. There are still advances in DRP where I will come back later on to improve the models we have for DRP. And that will help you to optimize the prediction you can draw from DRP measurements. So it is hard to tell who invented DRP first. I always like to recommend a publication from the ITWM of Kaiserslautern of Heiko Andre and other people which are well known in the community, for example, Mike Marsh, but also our CEO, Andreas Wiegmann, and Eric Glatt, our CTO, where they describe the whole procedure of how digital rock physics works in general.
Thank you for that.
Okay.
Oh, so this is our first polling question of the day. So I'm going to launch this first poll question, and what we'd like each of you in the audience to answer is, what rock type are you most interested in with respect to digital rock physics? Are you most interested in sandstone, or perhaps shale, or perhaps carbonate, or are you interested in something else? So select other in that case. So we'll give everybody a chance to answer. We have quite a few votes coming in. We have about 50% of answers, and keep shifting around, I guess. So we'll give another few seconds, and now I'm going to go ahead and close this poll, and I'm going to share the results with everyone. So the leader in this case is sandstone. Right behind it is shale, and then other types of rocks, and finally carbonate. So I'll stop sharing and send it back to Aya and Arne.
Mm-hmm. So it is, of course, great that you have proven workflows for sandstones. And I think that's why we have the result we have, because sandstone are very easy and well known that DRP is applicable to that kind of rock. Yeah.
Okay, so let's move on to the next question. So you're just explaining why CT can be useful in this industry. So the next question we have is, at what stage is a CT used in the development and production process of oil and gas reservoirs?
So usually you divide the oil and gas sectors into three categories, which are upstream, midstream, and downstream. And DRP is applied usually to the upstream sector, which is all about getting information about your reservoir, finding oil and gas deposits, but also producing them. And usually you would simply drill a core from your reservoir, or take cuttings, which you can get from your wellbore, and run multiple simulations on that after you have measured that sample with computed tomography. In the upstream sector, we would use CT and DRP to improve our well placement. So since you want to know how to place your well or your borehole in the best possible way, you would have to have the best amount or a huge amount of information about your reservoir. And you can get that by doing a lot of measurements from that reservoir. And one can be a DRP, but you can also use well logging and combine that with experimental approaches. But everything helps everything that helps you to get more information is very valuable for you as reservoir engineers. As I said, this helps you to characterize your reservoir in terms of porosity, permeability, but also saturation, exponent, formation factor, and so on. And that can be used in all three of the production phases you have during the oil production. That will help you ultimately to reduce the uncertainty and the risks you take when you drill a borehole. Because with more information, that provides you insight into your reservoir, and you can then place your well much better or adapt your production process to the information you have. And that gives you predictions which are valuable for management decisions. Like I said, for example, how to place your well bore, or which process should be used for your secondary or tertiary production environment. So in a nutshell, the results taken from computed tomography would lead, in the best case, to more efficient and effective exploration and production in your oil field. And besides that, you can use DRP in the research and development area to refine your methods you're using in DRP and CT environments. And that could be calibration of your simulations. If you have very complex geometries, you can calibrate them so that you would get the validated results, which are proven to be right. And based on the information you have then, you can develop the new workflows and challenge the barriers of what is possible with DRP at the moment. So it may be in the future even, I guess it will be better in the future, because all the methods we have in DRP are advancing while we're talking. You know? And that will allow you to gain new insights on rock properties which are valuable for your production environment. Any questions here?
Yeah, we have a question. You mentioned well placement in the upstream sector of oil and gas application. What are the signs of good and bad well placement?
Mm-hmm. So bad placement would be, you know that you have a high porosity at a certain location in your reservoir, and you decide to drill there, but then you find out during production that the permeability is far lower than expected. And then of course you have a high porosity, but no permeability to connect to all the oil which is there actually. And then the production is not as good as it could be if you have placed your well at another location.
That's really interesting. Thank you.
Mm-hmm. You're welcome.
Hey, so the next question, this is the one I always had and I always wondered about. So when you do CT scan, usually you're looking at pretty small plug, let's say. So the question is, how do you scale the CT analysis results to guide a decision-making applied to, at the end of the day, kilometer-sized reservoirs?
Mm-hmm. Yes, so DRP is almost every time about upscaling the data or the results you obtain from digital rock physics. When we start from the plug scale, which is usually the scale on which you would run micro computed tomography measurements, you have, of course, only a tiny bit of your reservoir represented in that plug. And since you want to know the properties of the whole reservoir, you have to upscale the information you get on a very small scale. And if you go even lower, you go even to the nano resolution area where you have clay minerals resolved. And if you have now a sandstone available which has a lot of clays inside, you may need to resolve the clay invariance as well to be able to upscale that information to your plug scale. And going one scale above, you are moving to the whole core scale where you only see the gray values that are changing. You can see these gray values changing here by layers. And of course, layers with darker colors have a higher permeability and usually porosity than these layers you are having, which are very bright gray values. And then what you can do is you take subsamples out of that whole core scale, measure them by micro-CT with a good resolution, and then you try to map the permeability you have on the plug scale to the whole core scale. And that can be done by mapping the gray values directly. So for example, you have a gray value area here, you take the sample, and then you know the permeability, which is most likely to be representative for that gray value area here. And then you can take another sample of these darker colors here, and then the permeability may be higher, and then you map that back to your whole core scale. And going even further, you can also use that information you have on the plug and core scale to insert that into integrated upscaling workflows of digital skull and lab skull results. So in this example, I have taken a figure from Burmeister et al. From the EAGE. I think it was in Madrid last year. This year it would be in Vienna. And they show how they integrated DRP data into their prediction of relative permeability on log scale. So if we are here in the centimeter scale, we move forwards to the meter scale. And even there, DRP gives you valuable information about your reservoir. And if you can then go one scale above, you are in the reservoir scale, which is like the kilometer scale. And of course, you would have some uncertainty left there as well. But if you insert the data you have gathered all over these scales here and feed that into your reservoir scale simulator, it may give you a very good approximation of how your reservoir will behave. So are there any questions here?
There is a question, but that's really interesting how the digital scale and the lab scale was matching right close to almost identical in your example. There is a question, do you scale experimental data in the same way by mapping data from small plugs to large cores into a reservoir?
Mm-hmm. So the good thing about simulations is that it's all about resolution and field of view. So if you have computers which are large enough, you can model very large reservoir scale models. And with experiments, what you get is a dedicated result for only that sample you have. You can, of course, try to upscale that as well if you know the location where it was taken from the reservoir. And then you can, of course, use also experimental data to insert the results you have to your reservoir scale. Yeah, of course, that's also possible. The advantages of the simulation approach would be that it is that the scalability is very good simulations for obvious reasons. Okay, any more questions to this slide here?
No, can move on to the next question.
Okay, thank you very much.
That takes us to our second poll question. So let's launch that for the audience. All right, so the question here is, which aspect of digital rock physics do you find the most challenging in advancing it to the production level? So is your challenge the data acquisition and processing portion, or is it lack of standardization and best practices? Or instead, do you find the challenge with integration with reservoir modeling workflows, or instead is the challenge transition from conventional lab scale to digital solutions? So we'll give everybody a chance to indicate what their challenges are, what their challenge is, most significant one is. And we've got about 40% of you voting. It's closer.
I think this question takes a little bit of time to think.
It
right?
does, right? You to really think about, all right, where is my challenge? And I guess it probably depends on what sector you work in as well. So, all right, we'll give a couple more seconds, 3, 2, 1, and I'm going to end this poll and share the results with you. And it looks pretty even. So the majority answer is balanced between both data acquisition and processing, as well as integration with reservoir modeling flows. And directly behind that, of course, is the lack of standardization and best practices and the transition from conventional lab to digital solutions. So it looks like there are problems and challenges everywhere is how I would interpret this, right? Very, very close in response. So I'm going to stop sharing and send it back to you guys.
Mm-hmm. So it's a good indicator of a new technology, which DRP is certainly. Yeah. So DRP is maybe used since the CT devices have a resolution about micrometer scale, and since the computers are only like since for the last 20 years powerful enough to handle that amounts of data, it is of course a very young technology, and that needs of course time to evolve and refine the methods you're using. Yeah,
for sure.
Okay, so that brings us to the lightning round. So in this part of the webinar, I'm going to ask Arne a bunch of questions, and those are not necessarily about X-ray, CT, or digital rock physics, but we want to do this to get to know the speaker. So you ready, Arne?
Yes.
Okay. First question. Where did you go to school?
Actually, I went to high school in Kaiserslautern, which is the same location where the company Math to Market is from. And that was a funny coincidence that I moved back to where I was born in. Yeah, because I've lived about 10 years in another area of Germany. And then it was like back to the roots for me in the end.
I guess you get to be close to your family and friends, right?
Yes.
So next question. What did you want to be or become when you were a kid?
So I grew up in the 90s, and there were a lot or many movies about lawyers. And since I didn't knew it better, which are my strengths when working, for some reason, I wanted to become a lawyer because I've watched many movies with that statements in the end, and then you win that case for yourself. And yeah, I was kind of impressed of lawyers by that time. Yeah.
Those are movie characters though, right? they all look impressive.
And I never wanted to be a firefighter or a policeman. No. No.
I wanted to be a lawyer too when I was a kid.
Yeah.
Yeah. It's probably not as easy as it looks in movies and TV shows, but
no.
Next question. What do you find most challenging about your job?
Mm-hmm. That is a very good question, because it challenges me almost like once a week. So when a customer comes to us and we talk to each other, the customers may not always be allowed to speak about all the data they have gathered. So sometimes you have to find out what the problem of the customer is by that time, without him being allowed to show you the data where he is doing the simulations on. And that can be quite complicated. Yeah.
I can see that being challenging.
Yeah.
Now, if you have your own lab And if you could buy only one imaging instrument, would you buy CT or SEM?
I would definitely go for the CT, because the field of view is much better and it is even scalable. So if you have a large sample, you can just put that sample closer to your detector, which gives you a better field of view to the cost of a worse resolution. And if you want to have only a tiny bit of your sample, you just put it nearer to your source, and then you can obtain resolutions of up to micrometers. Yeah. And
we certainly like that answer.
Yeah, I know. And FIB-SEM is often limited to a very, very small field of view, which makes it complicated to have larger scale features inside of your structures represented in FIB-SEM data.
Okay. So kind of building on that answer, next question is, will CT-based simulation replace experimental approaches in the future?
So hopefully yes, but I think it would be something like a complementary thing. So each of the approaches has their advantages, and one method may be better for one case, while the other would be better for the another case. And in the best case, I can even improve the quality of the data I get, for example, for simulations, by inserting something I know from the experimental approach and insert that into my model.
So I guess the experiments will never go away, but there might be better collaboration between the two techniques in the future.
Yeah.
Last question. How long does it take for a novice or beginner CT user to gain the expertise to use digital rock physics with confidence?
So when I started, CT devices were not bundled with the software for reconstruction, for example. So in my case, I've used a Procon Alpha computer tomograph and used software from the ITWM. And I think that became much better since the CT vendors are doing their own software, because then they just work better with each other because they know what they have to expect from each other. And then there may be integrated workflows where you can get everything in only one computer. And when I started, CT had their own computer and you had to do the reconstruction on another computer. So for me, it took like 1 year, but I think it can be much faster today.
I guess less than a year is not too bad to be comfortable with this technique. Well, thank you, Arne. I think we know a little bit more about you. Okay. So I think the next one is a question from us. Let's go to the next slide. Okay. So the next question is, when should we use digital rock physics and when should we use experiments?
Also a very good question. And we have also touched that in the beginning. So simulations are very good because they are non-destructive, because they are based on images which are obtained by microcomputer tomography. And that, of course, will allow you to run other experiments or simulations on the same sample without destroying them. And that is a huge advantage of the simulations here. Then you're able to model very complex processes that are difficult or even impossible to measure directly by experiments. So, for example, you would be able to observe time-resolved precipitation or dissolution within your simulations, which are hard to observe by experiments, because you can locally not resolve, for example, dissolution in experiments. Then they can be easily repeated and modified. So if you have produced some data which is based on a wrong model, you can easily take the same image stack and do a lot of other simulations on that to obtain the right result. And then it is very good if you want to optimize the production and reduce costs. That is also true for experiments, of course, because it will decrease the amount of uncertainty you have inside of your reservoir. And then I've mentioned it earlier, the scalability. So the simulations are only, or the only barrier for more simulations is your computational power you have available. So in the era of cloud environments, you can of course go to the cloud and run hundreds of simulations at the same time to obtain simulation results in only hours. Or even if you go for easier simulations, minutes. Then the experiments have the pros that it is not necessary. It may be necessary if you have no high resolution images available, like for the case for sandstones, which have a very high clay content and you're not able to resolve them. You can do a direct measurement on the data you have, and then you will get with high confidence a good result out of that data. Yeah, provided that you did not do any mistakes in the setup of your experiment. There's of course always the user bias. And then you can use experiments as a supplement to validate your theoretical models and simulations, which I have talked about earlier here. I have written down here the examples as well, which I've already mentioned. Sandstones with high clay contents may require to do some experiments, while if you want to have a higher sample throughput, I would rather go for the digital simulation and not for the experiments which are limited by lab equipment. So in the best case, both methods are complementing each other and allows you to obtain the best possible results, which with high confidence for your reservoir. Any questions here to that slide?
We got a couple of comments and a question. They're really appreciating all the information you're sharing, Arne.
Thank you very much.
Our attendees, and you know, they're commenting on your slides as you're talking, so you'll see them later. But there is a question on comparing different. We talked about what's your favorite instrumentation in this space. Do you need Fib SEM, or are there other types of rocks that only need CT? Can you comment on that a little bit?
So I would use conventional computer tomography for simpler rocks like sandstones, and would go to the scale below only if it is necessary, and if your field of view, which is available to Fib SEM, for example, is large enough to cover all the features which are present in your structure. So there is a good publication from Mita Sengupta from Aramco Americas, and they were conducting Fib SEM measurements on, I think it was some organic matter within a structure, and they executed some elasticity measurements by simulations on that structures. And I think they were able to upscale that to match also experimental results. So it depends highly on the case you're observing, on to which CT or CT device I would go. Yeah. Sometimes it will be required to use Fib SEM to go to the nanometer scale. Sometimes the plug scale would be sufficient. And in the best case, you have a whole core scale where you already know the different permeability areas. And then you can use something like Darcy flow simulations, which are also available in our software to compute the permeability on a whole core scale. So this is about like 13 centimeters wide in diameter then. So like that thick.
Thank you.
Okay, any more questions?
That's it for this one. We can move on to the next question.
Okay.
Okay, so we've been talking quite a bit about experiments and the simulations and their comparison. That kind of leads us to the next question. So how do you correlate the simulation and the experiments?
So this is one of the first things new customers ask us when they come from an experimental environment. They ask us, how can we trust your simulations? Because you can simulate anything and you will obtain some result. But how can we be sure about what the simulation gives us? And to prove that the simulations fit very well with the same approach in experiments, I have a slide here about digital and experimental MICP, which is mercury intrusion capillary pressure, where Stefan Berg, who is from Shell, conducted digital and experimental MICP. And what he found out is that there was, in the first place, a mismatch between the simulation here in red. So the red curve shows the simulation which was done in geodict, and I think it is a black curve. It's hard to tell here on the screen with the experiment. And then, okay, we are thinking about why can that be? Because the math is correct. And it is, of course, because the resolution for that sample was not good enough to represent all the features. In that case, the feature is porosity. Because if you have only partly resolved pore spaces available, you will always underestimate the total amount of porosity which is available in your structure. And if you now go for the porosity you can see, so in that case, we could see about 20% porosity in our software, but the MICP, of course, sees all the porosity that is there. And if you go now and put the porosity on the x-axis, you can see that the fit is very, very good, while the simulation does not cover that part of the unresolved porosity here, because it is not visible in the micro-CT scans. And what we did then is we implemented a Tumor fit, or a so-called Tumor model, which is also used widely in the oil and gas industry. And that allows you to approximate the amount of porosity you have unresolved in your structure. So by only computing MICP simulations on the structure you obtain from micro-CT, you can model the amount of unresolved porosity that would be visible in an experimental approach. And then the curves would be almost exactly the same. And we are also writing a publication about the quantification of the hidden porosity. And hopefully that will come out this year, and yeah, maybe in the early next year. And if you are interested in that, you can of course have that Berg et al. Article here opened and read through that paper. Yeah. Any questions here?
Yeah, I just shared that link, the Berg paper in the chat window for our audience to take a look at it. There is a question on required resolution for a good MICP data. Can you comment on that?
Mm-hmm. So it is always important to get the best possible resolution based on the field of view you need to resolve your structure. So there are different approaches, and they are highly connected to the model of representative elementary volume. And the idea behind that is you want to know how small can my sample be that it is representative for the whole surrounding area of rock. And if you know that size, you can then go for the highest possible resolution with micro-CT, obtain the images with, let's say, only 3 micrometer resolution, which is very good for micro-CT. And then that amount of unresolved porosity here will decrease. So that means there will always be unresolved porosity in your scans based on the method. That is, of course, always present. Since we have pixels or voxels in micro-CT data, they will always not exactly represent the real structure, but that small area you could not see will decrease by increasing resolution.
Gotcha.
Anything else?
Nope.
Okay, great. Then I will move over to the next polling question.
Yes, so this is our third and our last poll question today. So let's launch that poll. The question for the audience is, which area of digital rock physics research do you think holds the greatest potential for future breakthroughs? Is it characterization of unconventional reservoirs, or is it instead the ability to predict reservoir performance and recovery efficiency? Or is it instead, do you think the greatest potential is the investigation of multi-phase flow phenomena, or perhaps something entirely different? You can pick other. So we're going to give everybody a chance to get their votes in. I'm curious to see what the answer is for this one myself, for sure. We've got about a little more than half voting. We'll give a couple more seconds to allow a few more people to vote. We know you're out there. Yeah. And so we'll go ahead and I'll give you 1 second and I'll end the poll and I'll share the results. So the majority of people think that the greatest potential is in the ability for prediction of reservoir performance and recovery efficiency, followed by investigation of multi-phase flow phenomena. So I'll stop sharing and send it back to you guys. What are your thoughts there, Arne?
So I think that is not surprising, because the ultimate goal for DRP is that you want to maximize the extraction of oil from your reservoir. So it is not surprising for me. And the next thing for me would be the breakthrough in unconventionals, because often you have reservoirs which have multimodal porosity. And also our company has a lot of different models which we want to apply in the future to unconventional reservoirs. So I would have expected that to be the first or even the second result. But yeah, maybe that's only my personal opinion here.
Gotcha.
Yeah.
Or maybe you're a little ahead of, yeah.
Ahead of time, yeah. Hopefully, yes.
Yeah. That's why we do the polls, so we know what everybody else is thinking.
Okay, yeah.
Okay, so I think we have 2 more questions. This is second from the last. So what are the challenges you see as an expert in applying digital rock physics to a practical decision-making process?
So the first thing would be that you have enough reliable data available. And that can be obtained by using high quality CTs, for example, the ones Rigaku produces. And you need data which you're confident about. So for example, we take our sandstone with a high clay content. I would never compute any simulations which neglect that clay content inside of that rock structure and take the results for as a good validated result, because they would be wrong if I would neglect my clay minerals inside that rock. So in that case, it is always very important to know how much I can trust the simulations, because they always, anytime rely on the data you have available as images from your computer tomography. Then, and I've mentioned it also earlier, the computational resources. So nowadays we have huge computers available. So the digital rock physics models can also put more and more computational power inside of the simulations to be able to have fast and reliable results. And we can also use more complex models and have a result in only short amount of times. And of course, that requires also very efficient algorithms, where I'm convinced that we have one with the LIR solver in Geodict to work cost and time efficient, to have that advantage in comparison to the experiments. Then you have to be confident about the upscaling approach you're following. Every reservoir is different. So the integration of DRP results to the scales above is very crucial to have meaningful results. And in the best case, the model you apply to your reservoir fits the reservoir geometry very well. And then DRP will give you a lot of information about the reservoir, where experiments may not be able to resolve all the features you're interested about. Then validation is always a very important topic for us and our customers. We want that the company and reservoir-specific validation of the workflows is as easy as possible. And that is important because I've mentioned it earlier in the MICP. How do customers and how do we know that the results are meaningful and it's not only putting numbers together? So you have to account for different structures with different models. And the simpler, or maybe you start simple, and then you move forward to your more complex model, but you always have to keep in mind that the results should be created, that the results are meaningful in the end. Then it may be also important to automate your workflows. If you have a proved workflow from the validation section here, you want to maybe integrate that directly into your production environment by automation, where you have some kind of reservoir engineers, for example, and then they are doing that in an automated manner. So we, for example, have decided that we want to have a Python interface available for our software, where you can easily access all the data that comes from Geodict simulations. And then you can easily insert Geodict inside of your production workflows. Are there any questions to that slide here?
Yeah, so I was thinking the same thing that one of the audience member asked. Are there, which of these are the most challenging or difficult one in terms of data availability, computational resources, upscaling, validation, and automation? What would you say would be the toughest one out of all, or most time consuming? So
often the simulations are limited by resolution of micro-CTs. And that's why hopefully all the CT vendors are improving their devices so that we are going more and more to the nanometer scale, even with micro-CT, and they are inventing a lot of more algorithms to help you to get everything out of your CT data that is there. Computational resources is, I think, neglectable because computational power is, I would say, cheap today compared to 10 years or 20 years ago. That this is not the limiting factor. I would say the upscaling approach, which you are following, is very important because that is linked directly to the validation. So you cannot upscale something which you have not validated before.
Yeah.
So do the validation first, be confident about your model you're applying, and then you can try to upscale that and validate that upscaling approach as well. And automation would be the last part of the chain here. If you have done all these steps above, you can go to automation to insert that workflow directly into your production environment.
Yeah. It's interesting how CT images kind of are the foundation of everything else that kind of follows through after that. So really interesting stuff. Thank you.
Yeah. So of course, we can do a lot there by, for example, super resolution approaches. Yeah.
Yep.
So Rigaku provides us, for example, high quality input data, but we know that some features are hidden below that resolution. And then you can go and say, okay, I know I have this data sets here, which I've trained on huge amounts of other data where I know that the features are the same as in my structure I'm observing right now. And then I can try to upscale or do a super resolution AI algorithm there to improve the resolution I have to get the features visible in that structure. And then I can, of course, do the simulation on that super resolution image afterwards.
Thanks.
So this is our last question. And this is something a friend of mine asked me and I couldn't answer this question. So I'm going to ask you. So what is the difference between the regions in different areas, different countries that can produce oil effectively, or I could say cheaply, and the ones that cannot?
So as it is with simulations and experiments, the oil production is all about saving money for the barrel of oil you get out of your reservoir. So I want, of course, to have my production costs very low compared to the price the oil is valued on by the market. Yeah. So if I have an oil price of $100 per barrel, I want to produce the oil for maybe $20. Yeah. So that I have a very big amount of range where I can take my profits from. So it's all about reducing the costs for the production process here. And we have different regions, of course, on the Earth, where we have different burial scenarios for my organic matter, which becomes oil at last. One thing about the reservoir would be that the quality of your transport properties define how easily the oil can be extracted out of your reservoir. You can see that I have some pictures here of different structures. There is a fractured rock. There's almost homogeneous sandstone structure here, and the whole core picture I showed above, but also multimodal carbonate from the Middle East. And you can see that these are completely different. Yeah, every one of these has something that the others do not have. And that is also what I've mentioned about the reservoirs. Every reservoir is different. So you may have a very high permeability, but a low porosity. Then the amounts of oil I can extract from my reservoir would be also not as high as it would be with a high porosity and a high permeability. The other way around, if I have a high porosity but only a low permeability with no pore connectivity, I would also not be able to get all the oil out of my reservoir. So talking about the Middle East, this is a good example about of a carbonate from the Middle East. We have these macroscopic pores, and then we have these microscopic grayish areas of pores, which are only connected because we have also that macropores available in our pore geometry. And while the macropores provide you with a good connectivity, the microporosity provides you with the porosity you need to store huge amounts of oil in that rock compared to the volume that rock has. Then it is also very important what kind of oil you have inside of your reservoir. You could have highly viscous oil and low viscous oil. And of course, it would be much more difficult to get the higher viscous oil out of your reservoir than by only going for the low viscous oil. But since all these, or the history of the burial is different for almost every reservoir on Earth, I have to adapt my production to the properties my reservoir has. So there are some notes here on my list, like I would like to have favorable trapping conditions, which means that I would like to be able to drill that deep to get my oil out of that. I want to have a reservoir which is connected. I want to have a good reservoir source rock, which provides me with an oil that is easily to produce. And that is directly linked to the favorable history of burial and deformation of rocks in general. Any questions to that slide here?
Arne, so you kind of answered, there was a question on types of rocks found in different regions of the world, but as you mentioned on your on this, that there's different reservoirs and the oil depends on the reservoir. Are you able to predict the type of oil and reservoir in certain regions of the world, let's say North America or Middle East, based on where the reservoir is or the oil is drilled? Are you able to kind of predict, like, oh, this is in the Middle East, it's going to be highly viscous or not, something like that?
So this is something I would say is highly confidential for the companies. So as I've mentioned earlier, it is sometimes very hard to get information about the reservoirs. And that is why we are leaving our material database, where you can, of course, simulate oil flowing through your structure. We leave that database open to the customers. So you can define the viscosity based on the temperature, for example, by yourself. Yeah, so you can use your own input data where you have measurements from your reservoir. So all the customers know which oil they get out of their reservoir. But this information is often confidential. Yeah. Talking about the different regions on Earth, we have, of course, something like oil sands in Alberta, in Canada, where only bitumen is produced, and that is, of course, harder to raffinate after to put it into gasoline or so than by just getting the oil out of a reservoir from the Middle East. Yeah.
There's one more comment and question from the audience there. As somebody new to digital rock physics, what kind of advice would you give them to get more used to this field?
I would say increase the knowledge you have about your model and try to work on the confidence you have based on the data you have. So if you or deal with the expectations you have, that's maybe a better answer for that. If you expect to get everything out of a low resolution image of your rock, I would say you shouldn't expect that because the resolution is not high enough. If I know that I have a very good resolved image of my structure, I would say, okay, go for it and be confident about the results digital rock physics gives you. Yeah. But I think if I follow the learning curve when I start as a novice in digital rock physics, I would say try to improve on every aspect of digital rock physics, starting from micro CT imaging, or even maybe earlier from drilling the sample out of your reservoir, to micro CT imaging, to image processing, to simulation, and to validate your model. And then the topics I've mentioned earlier about be confident about your upscaling approach.
Thank you, Arne. This is all very helpful.
Thank you.
And the one thing to add just a little bit for the micro CT data collection part, we did another webinar last year about digital rock physics, and Arne joined us to provide his expertise there. And there's one episode that was mostly about how to collect the good quality data and also how to tell if you have a good resolution or enough resolution or not. So I'm going to put a link in the chat, and if you're interested in this part of digital rock physics, this one might be helpful.
Mm-hmm. Yeah, at this point, I would also do some advertisement for you, Aya, because you have been speaking on our yearly user meeting for Math to Market, and she described how easy it is with micro CT to obtain meaningful data. Yeah. Maybe
it's not as difficult as you might think it is. Yeah.
Yes. Yes.
Yeah.
So, okay, if there are no other questions, I would like to move forward to the next slide. Yeah. So, Aya, Angela, and Viral gave me also 2 slides to show what Geodict, the software from my company, is able to do with your data you obtain from microCT. So we cover the whole workflow or the whole process of digital rock physics with our software Geodict, starting from image import, where you can use micro CT scans, core CT scans, synchrotron CT, but also other imaging techniques, basically everything that produces an image. Then image processing, which is all about filtering, removing artifacts, and so on. The segmentation, where we provide you with also AI approaches to get all the information out of the gray value histogram you obtain from microCT. And then, of course, geometrical approaches to determine how much porosity do you have in your sample, pore size distribution, fracture identification, everything you can do on the morphology of your structure. And there we are one of the market leaders, the property simulation predictions. So our LIR solver, for example, is very good in predicting the porosity and also predicting the conductivity of samples. And we are moving even forward to put that also to the mechanical properties. And I have one last slide only about simulation approaches we offer with our software. We have solvers that solve one-phase flow problems, and that allows you to compute absolute permeability with a Stokes-Brinkmann or Navier-Stokes-Brinkmann approach. And our solver are efficient that they can be even run on structures that are 4,000 to the power of 3 voxels big. So a huge amount of data we are talking here about. But we also have applications for two-phase flow properties, where we're using the pore morphology method to compute capillary pressure curve, relative permeability. And we also have an approach where you can even consider mixed wettability. So if you have alternating primary drainage forced imbibition or spontaneous and forced imbibition, secondary drainage. And that is always under consideration of the entire contact angle range you would have when wetting your sample with oil or water. Then you can determine electrical and thermal properties. And looking on the time, I'm almost 5 minutes over. We offer also solutions to determine mechanical properties. And one of our newer approaches is, since we're all dealing with carbon dioxide in the atmosphere, we have also a solution for CO2 sequestration or CO2 deposition in rocks. Are there any questions to our software here?
Just an FYI to everyone, I have added the geodict link and the industrial application software links that aren't just mentioned in the chat window.
Yeah, thank you, Byron. Okay.
Well, we're a few minutes over, but I want to thank everybody for joining today's session and sticking with us. Next month, don't forget to join us for another simulation webinar with filtration application, again with Math to Market with Dr. Philip Eichheimer. Till then, take care and keep scanning.
Bye, everyone.
Bye, everyone. Thank you.
Thank you. Bye.
Bye.